So welcome to another one in the JKTech webinar series. My name is Matt Weier. Today I'll be discussing quality assurance in metallurgical testing. Just what I'm going to discuss today. I'll start with a little bit about JKTech and myself. I'll move on to a discussion of quality assurance, quality control, and analytical testing and accuracy in general terms, and then get into more specifics about metallurgical testing. We'll discuss the distribution of results and error characterization, just touching on error in analytical measurements. Following that, we'll move more into metallurgical testing, talking about the results, a little bit of the use of the results, and the significance of accuracy and consistency in metallurgical testing. After that, we will get into some of the real body of what we can do to have assurances in quality in the results that we get. I have mostly aimed this presentation as for clients who are getting metallurgical testing done at a laboratory and what they should do to try and have confidence in those results they're getting back from the laboratory. A little about JKTech. We offer a range of services over most of the mining industry, mostly consulting and laboratory services. We have our specialist software, JK SimMet and JK Float. Our specialist equipment, obviously being the JK drop weight tester, which is something I'm very much involved with. And we present professional development courses and webinars like this to try and help educate and inform the industry. We are very closely aligned with the Sustainable Minerals Institute, and in particular the Julius Kripschnitz Mineral Research Center. Technically, we are their technology transfer company. But yes, this very close working relationship means we can leverage all the expertise from all the groups that make up the SMI. As to myself, I've got a Bachelor in Applied Science in Chemistry from this century at least. My background is in mineral characterization. Back in my uni days, that was a lot of XRD and vibrational spectroscopy and some thermal analysis. After that, I moved out into commercial analytical testing and got a good background in what it takes to be an accredited analytical testing laboratory, and got to do some development of testing methods that then got accredited by our national bodies. Following that, I moved to JKTech in 2012. I did start in the lab and got my hands dirty doing some of the metallurgical testing before getting moved over to focus on the JK drop weight and SMC tests. And yeah, that's been my focus for about a decade now, working with all those laboratories around the world who are licensed to perform the JK drop weight and the SMC tests. So quality assurance, quality control, what is it? I just grabbed a short definition from Wikipedia. It's a great starting reference point. But in short, quality control is about being able to trust the results, being able to have some confidence that the results you're getting are accurate and reliable. So how do you do that? What processes can you have to ensure that you're getting accurate results. So I just want to step back and talk about analytical testing in general. Analytical testing involves your unknown sample or the sample of interest, and you do something to it, you put in a piece of equipment, and that gives you a response that is dependent on the sample properties. Obviously, the most basic example would be putting a sample on a spring balance and the response being how far that spring moves, which depends on the mass of the sample. Obviously, as we get into more complicated testing techniques, there's multiple measurements and multiple responses that are combined to determine the desired property. Obviously, a good example of that will be the bond ball mill. That's an example I'll keep coming back to. I trust that a lot of you are familiar with the bond ball mill test. It's probably the most common metallurgical test, so it'll be a great touch point for us. But yes, the bond ball mill test involves measurement of your feed size, your product size. It involves mass measurements. It involves measurements of the amount of material ground per revolution, and all those feed into the work index, which is what you get at the end of the bond ball mill test. With experimental measurements, you never keep getting the same answer all the time. If you have a sample and test it repeatedly, you end up getting a range of results. Most testing techniques will give you a range of results that are in a normal distribution. So what this can allow, it allows some characterization of what we can refer to as the error of the test. What we use and what is a common one is the 95% confidence interval. That's the range that covers 95% of the population. So if you get a value back from a test method and you know that 95% range, then you can be sure, or you can be 95% sure that the value you got is within half that confidence interval from the true value. So yeah, so what that does is that lets you know how far you are away from the true value from your test method. Now, in terms of accuracy, accuracy being how close are you to that true value? How close are you to getting a result that is the true property value? Most analytical test methods, they ensure accuracy by using calibration. And that calibration uses a certified reference sample. A reference sample being a sample where the properties have been very well characterized and known. And that way using a known sample, and you can relate that to the instrument response that you get. And that gives you a calibration curve. And then that calibration curve describes that relationship between instrument response and material property. Again, the basic example, going back to that spring or going to a mass balance, most labs will have a certified mass, a 1 kilo mass or a different mass. You put that on your scales and you basically dial it in so your scale reads 1 kilogram. And that's how you confirm, or that's how you set the accuracy for your test method. One thing to note is this does not happen in metallurgical testing. There is no standard sample that we know it has a work index of, say, 15 kilowatt hours per ton. There is no sample where we know it has an A times B of 50. So that is one of the issues with metallurgical testing. We cannot use these traditional or these standard techniques to ensure the accuracy of the results. So what can we do? We can't use the techniques that a chemist or a physicist would use to get the accuracy of their results. And also, how much of an issue is that? Given how metallurgical testing results are often used, there can be made a good argument that the accuracy of the results is probably less important than the consistency of the results. Most users of the results will be developing their own models, and those models usually have some sort of fudge factor or calibration factor in there to correct for any inaccuracies, or just to relate the different situations between what happens in the lab and what happens in the labs in the real world size. An example of this, which actually just came up in discussions here this week, we've been discussing the bond rod mill and differences between different labs in the equipment that they use. And we know of engineering labs that will have different factors depending on which lab they're getting their results from. So if that engineering company is getting their bond rod results from lab A, they'll use a slightly different equation than if they get the results from lab B, which relates back to the differences in the equipment and the differences in the liners used in the rod mill. The comment was made to one of the testing labs is, why don't they change their liners to what they should be? And the response being that that would lead to a step change in the results they provide, and they're more interested in providing consistent results than changing to what may be a more accurate method. And so really, when we're talking about the quality assurance of medical and metallurgical tests, we're probably more ensuring that the results are consistent. There's been no mistakes made and no errors. And following on from this, we'll talk about a number of ways, both in what that can be done and also how we can look at accuracy and what we can do in terms of accuracy without those standard samples. So on the right there, the techniques we're going to discuss is comparative testing, aka round robins. I hope many of you are aware that JK performs round robins, and that is one of our main quality control and quality assurance techniques. I'll discuss using multiple laboratories to try and account for differences that arise between the different laboratories. We'll have a discussion about repeat samples. That is when you do duplicate samples as part of a program. I know a number of clients will do that. Say for every 20 SMC tests they do, they'll have one repeat sample in there as a check. We'll talk about getting to know the laboratory that you're using, getting to know their procedures, building a relationship with them. And finally, we'll just talk about review of the results and how that should be done and what you can gain by that. Now, a comparative testing program, often called a round robin, that is when multiple labs all get sent the same sample. And that way, when the results come back, they can be compared. It's comparative. It is part of standard quality assurance in analytical testing. Accredited laboratories will often take part in regular comparative testing programs against similar labs, and that gives each lab the assurance they're getting agreeable answers to their competitors. What we can do in metallurgical testing terms, it's a powerful way to look at the variance between laboratories, where that variance and where those differences are coming from as well, and put the numbers on what that would mean for a client getting that test work done. As I mentioned, JKTech, we organise regular comparative testing programs. We're trying to get them done every 2 years. Sometimes issues come up. It is quite a task to get samples prepped for all our labs and get them shipped around the world. But yeah, we do regular programs for the JK drop weight and the SMC tests. And in previous programs, we have included bond ball mill tests, which I'll use as a big example in this discussion. So here I'll discuss a little. You can see the plot on the right gives our comparative testing program results for the bond ball mill work index that we obtained in the last comparative testing program we did involving that test. Just as an explanation of that plot, along the bottom you've got the various mills that were used in the testing program. Most mills most labs used one mill. There was a few labs that had a couple of mills in there. Each mill was used to do 2 samples, and the 2 work index values received the top and the bottom of the boxes for each mill. So what you would hope is that for each mill you get a very small box. That is, your 2 work index values are in good agreement with each other. You can see that is the case. We've got a lot of little small boxes, but we do have a few there where the mill gave reasonably large differences between their 2 work index values. Following on from this, we now have a sample that has been very, very widely tested over using a range of laboratories and a range of equipment. So we can sort of now treat this as a standard sample and take the average value as the accepted value for this material. Essentially, this is about as close as we can get to a certified reference material in this field. By having a sample, having it tested as widely as we can, and then that average value is taken as the accepted value. For this program, we got an average value of basically 15.4 kilowatt hours per ton. And looking at that 95% range of results, 95% of the results were within 13.3 to 17.5 kilowatt hours. So that defines that 95% confidence interval for the test for this material. We use duplicate samples in our round robin because that allows a more thorough analysis. It lets us tease out how much of that variance, how much of the error comes from just the test itself, and how much comes due to differences from one lab to another. Our analysis from this showed that yes, there are actually systematic differences between laboratories. So yeah, so if you send a sample to one laboratory, you will get consistently different results to if you sent your samples to a different laboratory. So this raises the question of how many laboratories would you have to send a sample to have more confidence in what the average answer is and how close that is to that true value, to that average value. So a lot of this analysis, which I'm discussing now, was done by my colleague, Tim Viscara. He presented a presentation on this back at SAG 19, and I've just pulled out some of his slides. So as I said, that analysis showed that, yeah, there is systematic differences, and the differences between labs is greater than the differences you get just in a single lab, just arising from the test method. So he used the relationship shown in this to calculate that if you wanted a certain accuracy on your average value, how many laboratories would you need? So if you just sent your sample to one lab, you could be 95% sure that they were within, what was it? It was around 2 or 3 kilowatt hours per ton. It was about 14% as a confidence interval. If you send that sample to 3 labs and use the average value you got from those 3 labs, that brings those error bars down to 1.3. If you use 5 labs, you can bring those error bars down to 1. And if you use 20 labs, that will bring those error bars down to 0.5. So if you really want to look into the accuracy of a test and you really want accurate results, this is a path that you can go down. You can look at your test method, you can look at some different labs, you can use different labs, and you can keep chasing more labs and bringing your error bars down through multiple testing using different equipment. Obviously, using 20 labs, you would need a very good reason to spend that much money. But as you can see, even just using a few labs, using 2 or 3 labs can make a big improvement onto your error and that confidence interval that you can have in your confidence that you can have in that final result. Okay, a more simple one, and one that I see on a reasonably regular basis, especially for big projects, is repeat samples. So for every 10 or 20 samples that a client is getting tested, they will have 1 repeat sample included. That's a reasonably cheap and easy way to start looking at that sort of stuff and start getting some idea of what the variance is in your test. Obviously, if you've got 2 repeat samples and you get 2 significantly different answers, then that would indicate some issue in the testing, or most likely some error that has been made. Also, similar to the use of the duplicate samples in our comparative testing program, use of repeat samples lets you start to characterize that variance in the testing method and what that confidence interval is that you're looking at for your samples, and can start giving you some error bars on those values that you're getting from that test work. I would recommend this. As I said, it is reasonably simple and cheap, especially for large programs when you're running 100, 200, 300 sample programs for geomet testing, for example. Yeah, chucking in a few repeat samples is a great way to start looking at what you're getting at your results and start putting some numbers on those error bars and the variance that you see in the results. I would suggest another important thing that clients do is know the laboratory that you're sending your samples to. Talk with your laboratory, visit them if you can, look at their procedures and their equipment, discuss with them how well their procedures and their equipment match up to any standards that are there. I know with the Bond ball mill test, the parameters for the Bond test are reasonably well defined in Bond's original paper. So yeah, you can discuss with the lab how well their procedures match what Bond used, and just see what they can provide in terms of consistency and how they ensure that their testing remains consistent. You can discuss with them how they calibrate the equipment that they can. For example, every lab should be doing regular checks or calibrations on their balances. You can run, it is possible to get standard particle size samples for calibrating your sieves. So yeah, if the lab that you're using can provide evidence that they do these checks, that they do these calibrations on a regular basis, then that is one step to getting confidence that their results will be consistent and that they take quality control importantly. I've got there about having a metallurgist review their procedures, review their results, review the results you're getting. That's also in my next slide, so I'll discuss a bit more of it there. Yeah, I would recommend having a good relationship with your lab metallurgist, your contact at the lab, so you can discuss issues with them and they can help you determine what you want and what you need to do with your testing, and then you can question them about what they do for quality control. Finally, something I hope that all commercial labs do, or all labs do, is a review of the results they get. That is a large part of my job here, and one of our big quality controls for JK drop weight and SMC results is to have myself review all the results that come in, and having that experienced operator review results. It allows anything unusual, hopefully, to be noticed. It's also a guard against just mistakes and typos that can happen in data entry. Mistakes happen, typos get made, things get mixed up. And a lot of the time, having a second pair of eyes review that can catch a lot of those mistakes. So I'd hope that most labs review their results. They have an experienced metallurgist who reviews the results after the technician has done the test work, to just ensure that no obvious mistakes have been made and that the results obtained match what you would expect from the material that you're testing. Okay, so to sum up what we've done, Metallurgical testing is a little different to normal analytical testing in that we can't use reference samples and we can't calibrate, which makes determining accuracy of results problematic. But as I mentioned, the accuracy, the technical accuracy of the results often isn't as much of an issue in how we use metallurgical test results as just having the consistency of the results. So that comes out due to sort of the regression models and the equations that engineering firms and clients come up with and how they use the results. Probably the most robust method of really characterizing the comparative testing results and having a look at where variance comes from and the source of variance and error comes through comparative testing programs and to a lesser extent by the use of repeat samples. Obviously running a comparative testing program is a large undertaking, but from the client's end, having some repeat samples in large programs is a simpler way to start looking at those same issues. As a client, you want to know that your lab, you want to have good confidence that your lab has good quality methods, has good quality checks, and reviews their results. And by review, I'm not just talking about that final number, the final work index, but you want to review that entire set, the entire data set generated during the test work. And it's best to be reviewed by someone who's quite experienced with that test. Okay, so that covers what I wanted to talk about. I realized that was pretty quick, but yeah, I think that mostly covers what we can do as metallurgists and how we ensure consistency in our results and how we can stop errors from getting through our results and keeping them consistent. I'd like to just finish. This is more JKTech courses coming up. Hopefully some of you may be interested in. The next webinar at the next end of next month is talking about sampling. Sampling is quite important, in my opinion, when it comes to metallurgical testing. If you can't get your sampling right, if you can't have a representative sample, then there's not much point in doing the test because your answer isn't going to represent what you get in practice. Sampling is trickier than I think a lot of people realize, even when it comes down to just selecting particles and how to keep it consistent. So yeah, I would recommend that, yeah, if you're doing any lab work, yeah, that would be a good webinar to listen to. There'd be some important points in there. I know just from our work as well, sampling and the person doing sampling can have a significant effect on those final results that you get. In terms of other courses coming up, we have our comparative statistics course, which is one of our crowd favorites. If any of you want to come over to Perth, we've got one in Perth in October. If not, we're doing an online one in November, which will be available for everyone. We have some JK SimMet courses coming up. For those of you interested to learn JK SimMet, I'm pleased to see that in September, we're presenting one in Spanish for you South American people. Again, one in Perth and another remote one coming up next month. Finally, talk on value chain optimization. That's much more of a holistic approach where we look at your whole value chain from blasting all the way through to float and what can be done to optimize that. I will say, please look on LinkedIn. Please follow us on LinkedIn. All our courses, all our webinars will be advertised on LinkedIn. That's a great place to stay up to date with what we're doing. Okay, so I think that's it. We don't have any other questions. I'd like to thank you all for coming and being present at this webinar. I hope it was interesting and you've got something out of it that you'll be able to use and take going forward, and give you more confidence, or allow you to have more confidence in the results that you're getting and using in the metallurgical testing. Cool. Okay, so thank you everyone, and stay safe all, and hopefully we'll all hear from you again soon. Thank you.